One of the most difficult things in unsupervised learning is dealing with high dimensional data. Our examples up to now have been in 2 dimensions and 3 dimensions are relatively easy because you can just look at the data. But what happens when you get into, say, a 1,000-dimensional space or really even a 7-dimensional space? How can you visualize the data to understand if EM is failing because inherently there are not clear clusters in your data, or it's failing because you've got bad starting conditions or your sigmas on the underlying probability distributions in the E-step are too small or too big. And that visualization of high dimensional data is a huge challenge, and it's particularly a huge challenge when you're trying to do unsupervised learning and you don't know that you have clusters in your data. And the next 2 techniques we're going to talk about are going to be techniques that augment unsupervised learning techniques to reduce dimensionality to help both for visualization purposes and for the purposes of computational efficiency. The other tricky business with working in these very high dimensional spaces is that although the calculations we have been doing are relatively inexpensive, as your dimensionality of your data starts to increase, that expense becomes more and more and more, and the dimensionality reductions will also help with computational efficiency. So let's start, before we dive into the underlying techniques, let's start with reminding you of some of the most basic properties of linear algebra, which are basis representations. And we've already talked actually quite a bit about that throughout the semester, and so part of this will be a review. Let me remind you that when you specify some point in, say, a 2 or 3 or 4 or 1,000-dimensional space, you are representing it as just a pair of values xi, yi. So here in 2-dimensional space, each point here is a vector p sub I denoted by a tuple xi and yi in R2. Okay, now when I specify that xi, yi, I am making an implicit assumption. You and I have agreed that when we talk about R2 and R3 and R4 and R1000, we are representing these points with respect to the canonical basis. The basis vector is 1, 0, that's the horizontal axis, of course, and the basis vector 0, 1, that is the vertical axis. It's the same way when I tell you the number 24, you don't ask me in what base. We know that we're talking in base 10, and when we talk about vector spaces, we are talking with respect to the canonical basis. And in particular, that means that the xi, yi is really what it is xi times this basis vector plus yi times this basis vector. The same way that 24 is 2 times 20 plus 4 times 1, we just never say that explicitly. And this, of course, came up when we were talking about the Fourier basis, because the canonical basis is a perfectly lovely basis, but it is only one of many bases. The Fourier was another basis. Same thing with base 10. We can work in base 2, we can work in base 16, we can work in base 8. We make choices. And dimensionality reduction is going to be, the first set of dimensionality reduction techniques that we describe are going to be about choice of bases. So let's just refresh our linear algebra here and remind ourselves how these basis representations work. This is the canonical basis. It is not the only basis I could have used. In fact, there are an infinite number of bases I could have represented points in R2 in. This just happens to be the one that we've all agreed on. Here, for example, is another basis. What are the basis vectors now? They're the vector 1, 1 and the vector minus 1, 1. That's what I've drawn in red here. Let's first agree that this is a perfectly fine basis. And what do I mean by perfectly fine? I mean that every point in this 2-dimensional space, R2, can be represented using that basis, the same way that every point in this 2-dimensional space can be represented using the canonical basis. If I just rotate my canonical basis by 45 degrees, I've not lost any information. That's the same way as me saying I can represent all integers using base 10, and I can also represent all integers using base 2. Sure, there's no loss of information. Now, is this a good basis or a bad basis? Is it desirable or undesirable? Well, that remains to be seen. So now the question, though, is for each point xi, yi represented with respect to the canonical basis, what is its representation in this new basis represented by the vectors 1, 1 and minus 1, 1. This isn't like me asking you 24 in base 10 is what in base 8? What is the conversion? All right. First of all, I don't like basis vectors that are not unit length. This has a length 2 and this has a length 2. So to simplify things, let's go ahead and normalize these by dividing by their length. So it's 1 over root 2, 1 over root 2, and minus 1 over root 2, 1 over root 2. So I've just shrunk them down a little bit. By the way, notice that these are perpendicular. That wasn't an accident, but it also wasn't necessary. I could have, as long as I pick two vectors that are not exactly on top of each other, I will represent this entire space. But this is still an orthonormal basis. The way the canonical basis is orthonormal, the way the Fourier basis was orthonormal. This is an orthonormal basis because these vectors now are unit length and they are perpendicular to each other. That orthonormality is going to become really important in a little bit, so hold on to that idea. So here's a thought exercise for you. Given some point xi, yi, represented with respect to the canonical basis, what is its new representation with respect to this new orthonormal basis, 1 over root 2, 1 over root 2, minus 1 over root 2, 1 over root 2? If you want, go ahead and pause the video and do this little linear algebraic exercise. It's a good exercise to remind you how you do transformations across bases. I'll give you a hint. We've already done it. We did it when we talked about Fourier, and we're going to do it again to remind ourselves. So go ahead and pause the video, and when you come back, I'll finish up. All right, let's solve this together. So let's see, what am I trying to do? I know xi, yi, that's my vector in the canonical basis. I've told you what I want to represent it with respect to a new orthonormal basis given by this vector and this vector. And I want to know how much should I scale these two basis vectors together such that when I sum them together, I get that vector right there. So AI and BI are my unknowns. As with any algebraic, any linear algebraic exercise, the best thing to always do is bundle up your unknowns and isolate them so you can solve for them. So let's bundle everything up. So I'm going to take my AI, BI and put it into a vector here. And notice that up here, AI is multiplying the first basis and BI is multiplying the second basis. So by putting the first basis into the first column of this matrix, that first column will multiply AI, the second column will multiply BI, and of course that whole matrix multiplication, 2 by 2 times 2 by 1 is 2 by 1, is equal to that vector right there. And so now I'm in pretty good shape because I've got a 2 by 2 matrix. I know it's going to be invertible. Why? I told you that these vectors are orthonormal. They are not linearly dependent on each other, and so I can invert the matrix and solve for AI, BI. Well, let's go ahead and do that. So you can just shove this into Python and solve for it numerically, or we can remind ourselves what the closed form solution is for a matrix inverse, which of course is just this right here. If I give you the matrix A, B, C, D, its inverse is 1 over the determinant, 1 over the determinant, AD minus BC, and then I swap the diagonals and I negate the off diagonal. So that is the inverse of the matrix. Let's apply that rule to the matrix here. So what is the determinant? A times D, so that's 1 over root 2 times 1 over root 2, 2 over root 2, which is just 1/2. And then I've got a minus 2 over root 2, but I've got a minus sign over here. And so that I get 1 over 1/2 plus 1/2, which of course is going to be 1. I'm going to swap the diagonal, negate the off diagonal, and this is my matrix inverse. So what is A sub I? The determinant is 1. So now it's this row of the matrix times xi, yi. So that's A sub I. And it's this row of the matrix inverse times xi, yi, and that gives me B sub I. All right, I've solved for the new representation from a vector that was originally represented in terms of canonical basis and now is being represented with a different orthonormal basis that's been rotated by 45 degrees. Notice something interesting here. So let me go back to the original matrix here, 1 over root 2. So this is my first basis vector and this is my second basis vector. And let's remind ourselves, let's walk through the general case of this first. So what we're going to do is we're going to take our new basis, are going to be in the columns of matrix M. This is the representation we're trying to solve. This is the old representation. And what we're going to do is we're just going to invert the matrix. Now, that's what we just did with the exercise. Now, remember that if M is orthonormal, then M inverse is what? just the transpose of the matrix. We saw that when we did Fourier analysis. So what that means is that AI, BI is just M transpose. We didn't even have to go to any of that trouble to do the matrix inverse. All we have to do is transpose the matrix. Transpose this matrix, what do you get? You get 1 over root 2, 1 over root 2 in the first row, and minus 1 over root 2, 1 over root 2 in the second row. And if you go back to the previous slide, you'll see that's exactly what we got. So the new bases are now in the rows of M. Because why? I've gone from column to row, which means that the new representation is simply the dot product with the new basis. That's really nice. So you have something with respect to a canonical. You have a new basis. If and only if that is an orthonormal basis, then the matrix inverse is the matrix transpose. And the way you find the new representation is simply take the basis vector and compute a dot product with the old representation. That's exactly what we did with the Fourier transform, because the canonical basis in space and the Fourier basis in frequency were both orthonormal. All right, so now let's go back to where we started. I have this P sub I. By the way, why do I want to change bases? Like, why am I dragging you through this? Okay, here it comes. I've got a bunch of P sub i's that are represented in a two-dimensional space with respect to the canonical basis. Perfectly good basis. I've now got a new representation with respect to this red basis, which is 1 over root 2, 1 over root 2. That's the diagonal one. And then minus 1 over root 2, 1 over root 2. That's this one over here. And of course, the root 2 is to make those unit length. And I've specified them to be perpendicular to each other. And you can see that by taking the dot product of these and seeing that the dot product is 0. So is there an advantage or disadvantage to this new representation? Well, let's find out. Let's take some point xi, yi. Now notice that these points all lie on the line y equals x. So for every point that I've drawn here in yellow, x sub I is equal to y sub I. And what does that mean? That means in this new representation, if xi is always equal to yi, well, the new representation is going to be whatever the x value is times minus 1 over root 2, plus whatever the whatever the value is, which is the same as x, times 1 over root 2, which means b sub I is always 0. Well, sure, you can sort of see that geometrically here. One of my bases, the one that goes along the line here, that's the A, and the other one is B. But all of the points are on this line here. And so what that means is I don't really need that other vector here, do I? I don't need this basis, right? So all of the B's in my new representation are 0. And all the A's are, well, whatever. It's going to be some point along this line right here. Now, why is that interesting? Well, because each P sub I in the new basis representation now only has a single scalar that I need to represent the value. I don't need two numbers because the second number is always 0. So why would I lug that around? Well, what have I done here by changing the bases? I've reduced the dimensionality of my data. I started in a two-dimensional space, but the points lived on a line. And if they lived on a line and I chose one of those bases to be along the line, well then that whole other part of the space is irrelevant to me. And now, instead of representing everything with two values, x, y, I only need one. That is the very definition of dimensionality reduction. And how did I do it? I did it by finding a new basis. In that case, it was an orthonormal basis, but it didn't have to be. I found a new basis, I projected onto that basis, and I threw away whatever I didn't need. Principal component analysis, so-called PCA, does exactly that, but it learns the best orthonormal representation to minimize any errors when you reduce dimensionality. PCA discovers an orthonormal basis for dimensionality reduction. The game here is going to be we're going to take data in some high dimensional space, and we are going to say we want to reduce the dimensionality to dimension 1, dimension 2, dimension 3, dimension whatever it is. So either we can visualize it or so we can have computational efficiency. What is the best way to do that where we are going to force dimensionality reduction, but we want to minimize any distortion in the projections? Now here in this case, there was no loss of information. because all those points lived exactly on a line. They, in fact, lived in a linear subspace in the original two-dimensional space. That's obviously a toy example. What happens when they don't? And then how do you find these new orthonormal representations so that you can work in a low-dimensional space but preserve as much information from the high-dimensional space as possible? And that's going to be the technique that we talk about next, which is PCA, Principal Component Analysis.